Hi everybody, welcome back to my channel on Feynman integration. Today we're going to be reevaluating that integral using King's property. I previously evaluated that integral using Feynman integration, and today I'm going to be using a different method, King's property, or a special case of King's property. This special case, to be specific. I think my next video I'm actually going to solve it a different way using a result that I got from a previous video, and that video is going to be weird, but you arrive at the same answer. Anyway, brief recap on this special case of King's property. King's property is this. It says that the integral from a to b of f of x dx is equal to the integral from a to b of f of a plus b minus x dx. Pretty easy to prove using a substitution. Okay, so now that we have that, let's just go ahead and apply that to arrive at here. So basically what we have is the integral from 0 to pi over 2 of a function that can be written purely in terms of cosine x and sine x. What that means is it's a function like this. Let's just say we've got e to the sine cubed x plus the natural log of cosine x over pi times the inverse tangent of secant x. So I know that's not cosine x or sine x, but it is because it's 1 over cosine x. So it would be a function similar to that, basically, where everything can be written in terms of either cosine x or sine x. And what it says is that if you integrate that function over from 0 to pi over 2, you can literally just switch every instance of cosine x to a sine x, and you must also switch every instance of a sine x to cosine x. So this would become e to the, keep in mind, as long as the bounds of integration are 0 to pi over 2. It has to be 0 to pi over 2. So this would switch to an e to the cosine cubed x plus natural log of sine x over pi times the inverse tangent of 1 over sine x. So that's how it's used. And I'll just go ahead and show why that's true really quick. First, we want to note that the sine of pi over 2 minus x is equal to cosine x. And vice versa. The cosine of pi over 2 minus x is equal to sine x. That's something that most people learn in trigonometry, and if they don't remember it from trigonometry, they relearn it in calculus, and if they don't remember it from calculus, they relearn it again in calculus 2, so it's very common. But anyway, so we have the integral from 0 to pi over 2 of f of cosine x sine x dx. So well, let's see. With King's property, which says that the integral from a to b of f of x dx is equal to the integral from a to b of f of a plus b minus x dx, let's just apply that to here. So we have the integral from 0 to pi over 2 of f of cosine of, let's see, a plus b is pi over 2. Pi over 2 minus x. And sine x, which is, and so we will change that to sine of pi over 2 minus x dx. So we basically just applied King's property to this, and now we recognize that, there we go, that this is just sine x, and this is just cosine x. So that's how you get that. So now I hope you all believe me that we can use this rule. All right, let's get started. So that's our integral. We make the substitution that x is equal to the tangent of u. And I picked that because I have x squared plus 1 in the bottom. And that always makes it a little bit easier when you make that substitution if you have x squared plus 1 in the bottom, because it will cancel out with, well, here, I'll just show you. So x is equal to the tangent of u. We all know that tangent squared u plus 1 is secant squared u. So this would change to a secant squared u, and then we would get back a secant squared u on the top from dx being equal to secant squared u du. So that's the obvious substitution to make. And you can arrive at this, making that substitution, with, as long as you know properties of logarithms, basically, and that you know that secant u is 1 over cosine u, and 1 over a is equal to a to the negative 1. But anyway, with that substitution, you can get from there to there. In the next step, all I did was multiply the top and the bottom of this by cosine squared u, and then used the fact that 1 minus sine squared of u is equal to cosine squared u to get this. Then I distributed and rewrote it as two separate integrals. So we have minus 2 integral 0 to pi over 2 times the natural log of negative 2 times the integral from 0 to pi over 2 of the natural log of cosine u over sine squared u du. And that comes from this, negative 2 natural log cosine u over sine squared u du. And this part is, let's see, we have a 2. So we have a negative 2 sine squared u natural log cosine u over sine squared u. The sine squared u's cancel out. I know this seems like I'm skipping a lot of work here, and I am. That integral will evaluate to pi. Negative 2 integral 0 to pi over 2 of the natural log cosine u over sine squared u du will evaluate to pi. You have to use integration by parts, and you really have to be comfortable with taking a difficult limit using, I think you have to use L'Hopital's rule 2 or 3 times to evaluate a limit. And there's 2 limits, actually, that you need to evaluate. But anyway, I'm sure you can all do it. Try it out. It's a tricky one. That would be a challenge question on like a bonus question on a test in Calc 1 or 2. But anyway, it will evaluate to pi, and you can figure that out using traditional methods. This one requires the use of King's property. And I suppose, I've already done that in a previous video, but I think I'm going to reevaluate it right now just for fun. All right. So let's call some integral j. It'll be equal to the integral from 0 to pi over 2 of the natural log of cosine u du. Utilizing this fact, we know that it's also equal to the integral from 0 to pi over 2 of the natural log of sine u du. So j, okay, so we have two expressions for j. So what we're going to do is basically add these two together to get 2j. So we have that 2j is equal to the integral from 0 to pi over 2 of the natural log of this plus this. Using the properties of logarithms, we can just say that that is 1 natural log of that times that. So we get cosine u times sine u du. So, how'd that help us? Well, we almost have a double angle right there. What we need to do to make it a double angle is this. We need to put a 2 right there. Well, you can't really do that without making some other changes to the equation. So you got to figure out, what did that actually do to the equation? Well, using the properties of logarithms, we know that all that did was add a natural log 2 to that equation. So we need to subtract natural log 2. There we go. Then we recognize that that is simply sine of 2u. Right? Okay. So let's just see. Let's immediately split this one off. Let's just go ahead and evaluate this one. So this will be, let's see, this will change to a du, and then we have minus the integral from 0 to pi over 2 of the natural log of 2 du. Well, that's just going to be pi natural log 2 over 2. Okay. All right. So now we need to do this one. Okay. Let's make another substitution. We're going to say that u is equal to w over 2. Therefore, du is equal to 1/2 dw. All right. Let's change it. Apply that substitution. We know that 2j is equal to the integral. Okay, so w is equal to 2u from that. So we actually have the integral from 0 to pi. And then natural log of sine w. Du is 1/2 dw. So we'll just write that as 1/2 dw. Well, what do we do now? I know. I'll do this. We're going to split that integral up into two different intervals. The first one going from 0 to pi over 2, and the second one going from pi over 2 to pi. Okay. Okay. So I'm not gonna really do a substitution on this one. As long as the substitution you're making is like your original variable is equal to a new variable plus a constant, you can pretty much you can do this. What I'm gonna do is I am going to subtract pi over 2 from this interval, from both ends of the interval. So what you get is the interval will change to 0 to pi over 2. But since I subtracted from the interval, I have to add to the argument. So this will actually be a natural log of sine of w plus pi over 2. What is the sine of w plus pi over 2? Sine starts there, goes like this. It starts here, goes like this. I know you're probably seeing this backwards. And then you add pi over 2, so it's a shift to the left. Pi over 2, that will make it cosine of w. Okay, now we're talking. Now we're in business. Okay. And of course, we also have this minus pi natural log 2 over 2. So we have 2j is equal to 1/2 natural log sine w dw plus 1/2 natural log cosine w dw minus pi natural log 2 over 2. Okay. Well, we use King's property on this one right here to switch that to a cosine w. So now we have 2 times 1/2 the integral from 0 to pi over 2 of natural log cosine w dw, which is simply j. So we have 2j is equal to j minus pi natural log 2 over 2. Subtract j from both sides. Gives you that j is equal to negative pi natural log 2 over 2. But we don't want j, we actually want 2 j's. And of course, 2 j's would simply equal negative pi natural log 2 over 2, giving us a final answer for I being equal to pi minus pi natural log 2. And that's the result we got last time. So there you go. Solved using King's property, and I know this integral is not trivial, but it doesn't require any special tricks. So yeah, there you go. Same result we got last time, written a little bit differently, but still the same. Hope you enjoyed that.